Principal Component Analysis, abbreviated as PCA, and Exploratory Factor Analysis, abbreviated as EFA, in SPSS for a data extracted from survey or questionnaire that is based on a 5-point Likert scale. If you find this video useful, do subscribe to the channel, leave any comment in the indicated box, and activate the notification bell to receive the recent and latest release into the channel of several different video clips, and click on the like icon and share the video link with others so the channel can expand and improve to include a large scope of different statistical method and how to analyze data using several different statistical packages such as SPSS, Excel, Stata, Jamovi, RStatistic, GraphPad, Prism, GPower, Python, and RevMan. Principal Component Analysis in SPSS, abbreviated as PCA, is a statistical method. It is a reduction technique that is commonly used to analyze data extracted or collected from a questionnaire that is based on a Likert scale, whether it is 5 points or 7 or 9 Likert scale. The objective of performing the PCA for a questionnaire data is to reduce the number of the items and group the items into groups or constructs or factors or components, and the items that are included in each component load together and hold together and measure the same construct. Here in this SPSS data view, I had inserted a data extracted from a questionnaire. I have only inserted, for the purpose of explanation, 9 items or 9 questions, and these questions the participant will have to choose from 1 to 5, so it is 5-point Likert scale. The respondent will respond by either selecting 1, 2, or 3, or 4, and 5. 1 for strongly disagree and 5 for strongly agree. There are 200 participants who filled the questionnaire. To perform principal component analysis and to try to find out whether some of these items can group together, can load together to represent or be part of a construct or a factor or a component, then the principal component analysis statistical method can be performed. And the way to do that in SPSS, click on Analyze, scroll down to Dimension Reduction, then select Factor for Factor Analysis, and then in the new window select the 9 questions or items and drag them into the area for variables. Here there are several selections that we need to choose from. Click on Descriptive. In the Descriptive window, tick on Univariate Descriptive. For the correlation matrix, tick on Coefficient, Significance Levels, determinant, and KMO, and the partlet test of sphericity. So all these are essential to take them on this window. Click on continue, and for the extraction, click on extraction. The method to use for extraction, there are several here. I'm going to stick basically for this video to perform principal component analysis, PCA. Click on that, and then keep the unrotated factor solution ticked in, and then tick on scree plot, and then click on continue. For the next icon, click on rotation. In the rotation here, for factor analysis method, there are two types of methods: orthogonal or oblique. Orthogonal is performed when the factors are not related, they are not correlated. Orthogonal include varimax, equimax, and quantimax. For the other type of method, which is when the factors are correlated, it is called oblique method, and that include direct Opplimin and Promax. And for the sake of this video, I'm going to select the oblique method, the direct Opplimin method here, and then I will click on continue. For the scores, no selection will be taken here. Click on continue. For options, tick on the exclude cases listwise, and for coefficient display format, tick on sort or sorted by size, and suppress the small coefficient, and I will choose that to be less than 0.3. Absolute value below than 0.3. Click on continue, and then click on OK. Several tables and chart produced. The first table shows that there are 9 items, and the mean and the standard deviation is calculated, and there are 200 participants, and there are no missing data here or values. The next table is an important table that shows the correlation matrix between each item correlated with the another item from 1 to 9, with a significant one-tailed p-value is generated here. What we want to look in this table is that the correlation between items should be in the range between 0.3 to 0.8. Anything less than 0.3 means that there are less correlated, or there is weakly correlated, and anything above 0.8, it indicates that the items or the questions are strongly correlated. So we don't want a very strongly correlated items, and the ideal is to have between 0.3 and 0.8. For negative correlation, the value should not be greater than minus 0.8. And if we look here, we can see that item 1 correlated strongly with itself, so it's absolute correlation, a value of 1 or the R. For item 1 and item 2, it is 0.65, and for item 2 and item 3, it's 0.4, and so on. What is also important from this table is the determinant. The determinant has to be greater than 0.0001. So the value of the determinant has to be greater than 0.0001. 0.001. So point, 4 zeros and 1. Any value of the determinant higher than that, then the PCA can be performed. And here we can see that the value is greater, it is 0.04, and that is the data can be considered for PCA. The second table is the table for KMO and Bartlett test. The Kaiser-Meyer-Oakland measure of sampling adequacy, the value for that has to be greater than 0.5. And here it is 0.55, which is acceptable. And the value for the p-value has to be less than 0.05. So we need this p-value to be less than 0.05, i.e. significant. So these two conditions has been fulfilled. So PCA will be performed for these data. The next table is for communalities. It shows that the communalities extraction values for each items represent the proportion of the variances for each variable that can be explained by the factors. Scrolling down to the next table here is total variance explained. The table shows that there are three components, component number 1 and 2 and 3. And those three components can explain 68.4% of variances. So the analysis has reduced the items and grouped them into three factors or three components or three constructs that can explain 68.4% of variation or variance. The next plot is the Scree plot. Based on eigenvalue, it shows that anything above the one value, there are three components generated, 1 and 2 and 3. Scrolling down to the button matrix, this table shows that three components or constructs or factors has been generated, 1, 2 and 3. The table shows that component 1 have three items. Item number 4 and 6 and 5 load together and grouped under the component 1. Here we are looking for a higher value, a value greater than 0.45. The cutoff point the cutoff value is greater than 0.45. And as we can see here that item 4, 6 and 5 load together and they have a strong value here. And as it's shown here, the next component, which is component number 2, there are three items that load together strongly. The value is 0.9, 0.8, 0.79, and this component or this factor or this construct include the item number 1, 2 and 3. Moving to the component number 3, there are three items that are grouped into that factor or construct: item number 7, item number 9 and item number 8 with a strong value of 0.8, 9.7 and 0.6. So the PCA had grouped the 9 items or questions into 3 components or construct or factors. Each component have 3 items in it for component number 1, 2 and 3. These items hold together to be part of a construct. Moving down here to the last table, which is the component correlation matrix. This table will shows the relationship between the components or the factors or the construct. Here we will look for any value of greater than 0.32 that can indicate that components are correlated. And as we can see here, nothing is higher than or nothing greater than 0.32. So from this table, it is clearly shown that there is no correlation between component 1, 2, and 3, or 1 and 3, or 2 and 3, which will give us a hint, an indication to go back again and repeat the analysis or the PCA analysis. Choose a rotation method which is for uncorrelated or unrelated factors, such as the orthogonal method can be Varimax, or it can be other methods. This is the way to perform PCA analysis in SPSS for data deduction for an instrument or a scale that is based on 5 Likert scale or any other scale in SPSS. Exploratory factor analysis, abbreviated as EFA, or alternatively can be called as principal factor analysis or common factor analysis. In SPSS, it is designated as principal axis factoring, is a statistical or mathematical method that is commonly used for the analysis of data extracted from a questionnaire or a survey. And these data, the response in it is measured at 5-point Likert scale, in which the participant had an option of choosing from 1 to 5. 1 stands for strongly disagree and 5 for strongly agree. The objective of performing EFA in SPSS is to group questions or items that has been developed for an instrument or a scale, i.e. a questionnaire, to group these questions into factors or constructs, and to find out whether these items load together or hold together to measure certain or specific construct or factors. So basically grouping the collection of questions into factors or constructs. Here in SPSS data view, I had placed data in which the participant had questions, items to answer, and he had or she had a selection from 1 to 5. So this questionnaire was based on the 5 Likert scale, and I've just selected here 8 questions or items for the purpose of explanation. There are 200 participants who filled the questionnaire, and their response were recorded. To perform EFA, exploratory factor analysis, to find out how many factors or construct these items can be grouped into, and to find out whether these items can, some of these items can load together and be grouped into specific factors or construct, to measure that construct without specifying the construct itself. So the objective of performing the exploratory factor analysis is to produce or group these items into factors or constructs, and for the researcher has to give these factors or constructs a proper labeling or naming. To perform the analysis in SPSS, click on Analyze, scroll down to Dimension Reduction, and then click on Factor. Here a window appear. In the window, select the items from item number 1 to item number 8. We're going to select them, all of them, and then drag them and move them to the variable box here, or variables box. There are several options to select from here. Click on the icon for descriptive. In this new window, tick on the univariate descriptive. For the correlation matrix, tick on the coefficients, tick on the significance levels, which is an optional, can be presented. Tick on determinant, which is an important, and tick on the KMO and Bartlett's test of sphericity. Click on continue. Now for the extraction method, here we need to specify which method to use. SPS has several options to choose from: principal component analysis to exploratory factor analysis. For exploratory factor analysis, click on principal axis factoring. Keep the tick for unrotated factor solution. Tick on the scree plot, and for extract based on eigenvalue, keep that at a 1 value. Eigen's value or eigenvalue is greater than 1. However, if you have already done a principal component analysis and you have an idea that you would have 3 or 5 factors or construct, then you can specify that, but for the sake of this video I will just keep it empty. Then click on continue. Click on rotation. In the rotation here, there are several methods to choose from. There are 2 types of rotations: orthogonal, which include the varimax, quartimax, and equimax. And the second type is the oblique rotation, which include the direct oblimin and the pro-max. The orthogonal rotation is used when the factors are not correlated, and the other type is used when the factors are correlated or associated, or there is a strong relationship between them. So for the sake of this representation, I will stick for the direct oblimin, which is an oblique rotation, and I will click on continue. For the scores, no changes, just click on continue. For the options, keep the tick on the missing value, exclude cases list-wise, and for coefficient display format, tick on sorted by size, and for suppress small coefficient, tick on that, and I will insert a value of 0.3. Click on continue. Several tables and a plot are generated in the output for the SPSS, as shown here in the descriptive statistics. A mean and a standard deviation is given for each item, and there is no missing value or values for each item here, as the total is 200 participant. The next table is the correlation matrix. For this table, it is important that the value, which is the correlation between items, item number 1 with item 1, item 2 up to 8. So this is called correlation matrix, and the value need to be between 0.3 and 0.8. Anything above 0.8 will be a high correlation, which might indicate a strong correlation. Anything below 0.3 considered to be a weak correlation. So the ideal is to be between 0.3 and 0.8 for a positive value. For minus value, the correlation should not be less than minus 0.8. And if we look here at the values, item 1 correlate with 2 at a value of 0.65, with 3 is 0.62. However, a correlation between item 1 and item 1 is absolute correlation, which is 1. And that is as shown, correlation between item 2 and 2 and 3 and 3 all have a value of 1. What is important also from this table is the determinant value. The determinant value has to be greater than is 0.00001. So the value has to be higher than 4 point and then 40 and 1, and the value here is okay to proceed with the EFA analysis. The second table is the table for the KMO and Bartlett test. The Kaiser-Meyer-Olkin measures of sampling adequacy. The value has to be greater than 0.5, and here it is 0.57, which is acceptable. And for the p-value, it has to be less than 0.05, and it is here the p-value is significant. Moving to the third table, which is the communalities for the extraction for each item from item number 1 to item number 8. So these extraction values shows the proportion of the variance for each variable or each item here, which is the item 1 to 9, that can be explained by the factors. The next table is the table for the total variance explained. So here it shows that there are 3 factors, 1, 2, and 3. 3 factors can explain 72.26% of the total variances. So the EFA analysis had grouped these 8 items into 3 factors or constructs. And those 3 factors can explain 72.2% of the total variance. Moving to the next plot here shows the Scree plot, in which the eigenvalue was set at 1, and there are 3 factors, 1, 2, and 3, that can be extracted. Scrolling to the, not to the factor matrix table, but to the button matrix table. From this table there are 8 items, as shown here from 1 to 7, misarranged. There are 3 factors extracted. So those items, 8 items, has been grouped into 3 factors. Starting with the first factor, which is factor number 1, have 3 items load together for that factor, and the loading value is very high, 0.96 for the first item. For item 2 it is 0.67, and for item 3 it's 0.65. The value for the loading factor here has to be greater than 0.45 as a cutoff value. So these 3 items hold together and load together, and which indicate that they are measuring specific construct or a factor. But what is the factors? it is not determined. The researcher has to determine the label or the name for that factor. The second factor that has been produced, which is factor 2, which contains item 4, item 6, and item 5. All these three load together into that factors, which indicate that they measure that factors, and the loading factor value is high 0.98, 0.6, and 0.57, which is acceptable. The third factor or construct holds in it two items, item 7 and item 8, with item 8 of a loading value of 0.88, and for the 7 is 0.58. So this analysis has shown that those 8 questions or items can be grouped into 3 construct or factors, so they can measure those factors or those constructs. One important observation is the factor correlation matrix table shows the correlation between the factors. Any value of greater than 0.32 that indicate there is a correlation. And here from the table it's clearly shown that those factors are not correlated. So then we can go back again and click on factor analysis and look for a rotation that is for not correlated factors, which is the very max. If I click on the very max to repeat, redo, rerun the analysis, EFA analysis with an orthogonal rotation, which is for the uncorrelated factors, click on continue, click on OK, then the similar tables are generated here, showing the descriptive statistics, the correlation matrix here with the determinant value stays the same here, and with the KMO 0.57 and p-value less than 0.05, and again 3 construct has been generated from this analysis that explains 72.2 total variances as shown here in the scree plot. And if we scroll down to the rotated factor matrix, again 3 factors. The factor 1 has 3 items in it, factor 2 have 3 items, and factor 3 have 2 items in it. So this is the way to perform exploratory factor analysis. If you are a student or a researcher and you have a data, whether it is quantitative or qualitative, and you want to perform statistical analysis on that data using any of the softwares listed here, whether it's SPSS, Excel, Stata, Jamovi, RStatistics, GraphPad, Prism, RevMan, GMP, Python, then do contact me to arrange for either a one-to-one private tutor session or a training course on any of these statistical packages. My contact details are given here, so don't hesitate to write to me or email me if you need a private one-to-one tutoring or a training course.